Welcome back to Math 345. This is one a day 18. In this video, we're going to cover several examples that span, of course, across the breadth and depth of this particular one a day. To get us started, then, let's look at example one. So in example one, we're looking at the expected values with the parameters b0 and b1 for the given y values. We want to find a form of this that is the difference of those pairs, and we're trying to maximize or minimize this particular quantity, this expectation value. And so to do so, we'll take the partial derivatives of f with respect to b naught, and then f with respect to b1. We'll set these partial derivatives equal to 0 and solve for the critical values. So in doing so, the partial of f with respect to b naught gives us 2, and then the sum yi minus the value here times the value of -1. Since we're taking it with respect to b1, the term here gets a -1 from the minus sign here. And so if we set that equal to 0 and solve, we end up with, by moving the expected value over, we have the expected value of, or the sum of the individual values is equal to the sum of the b naught plus the sum of the uh, linear term bi, so the slopes, if you will, times the xi quantities. And then the partial with respect to b1 gives us a very similar form. In fact, this part is exactly the same. The only thing that's different is the minus sign coming from here. It looks like I'm missing a minus sign there, actually. Uh, Add that there. Forget to distribute. But here multiplying that, so there should be a minus sign in there. Or I could put the parentheses around it, obviously. And then the partial with respect to the b1 here gives you the xi terms. Setting it equal to 0 and solving, you have the sum of the mixed terms, the yi xi terms, which are here. And then you have the b not xi and then the b1 xi squared. Okay, so from those values then, we have the quick values. We're going to make the substitutions that sx is equal to the sum of the xi values, and then the sy is the sum of the y values. And likewise here, we're going to have the sum of the xi values, the sum of the xx, which means that this is x squared, and then the sum of the xy values. It's just shorthand, so we don't have to write the sums out all the time. And so we put this into a linear system with the b naughts and b1s, or with respect to the b naughts and b1s. We're trying to solve for these values here, and so we can simply use any number of methods to isolate the desired variable. So if we do that, we can simply move this over, and we can use Cramer's rule, which is what we're going to do here. So the determinant here is the overall determinant, which we'll be using in just a second. And then for B naught, you're going to replace the column that you're looking for with respect to, and then the other column that's still there. So we're replacing this one. And we take the determinant, we get this value. And likewise for B1. Okay. And so then we just divide by the determinant, and so we end up with our parameters have these values. So B naught and B1 have these forms. And then finally, substituting it back in part 4 here, in part 4 here, with the identification of these substitutions, then we can express B naught and Bi, or B1 in these new, and so we get that our equations are here and here, and that simplifies nicely, at least a little bit in terms of writing it out. So you have sy times sxx minus sx times the mixed product times n times the sum of the sx squared, which is this term. And then this b1 is just simply the sum of the sxy terms divided by the sum of the sx terms. Okay. All right. So that's it for example one. I hope that was helpful. And now we're going to move on to example two. Okay. In example two, the problem is asking about, let's go back to example two. Okay. So it says that there's a dealership, a quick sell car dealership, and it has been using 1 minute spots or spot ads on a local TV station. The ads always occur during the evening hours and advertise the different models and price ranges of the cars. There's a 5 week period, and they want to know what the results are for a line of best fit, given that those values. And so let's go ahead and so they give us a table to fill out, and they give us the 5 weeks of data. Okay. And so we're looking to fill out the table. So we have the x squared, the y squared, and then the xy terms. And again, we need these quantities for the linear fit. And then we also have the sum of each of those quantities squared. Okay. So as we saw in example one, then our B naught is this relationship, and our B1 or slope is this relationship. So to simplify everything, we can just plug in those numbers. So SXY is 1400. 1400 minus 62 times 98 divided by 5. That gave us 184.8. SSX is 924 minus 62 times 62 divided by 5, which gives us 155.2. Okay, so that gives us then that B naught is 98 times 924 over minus 62 times 1400 over 5 times 155. So that gives us that B naught is equal to 4.835, and B1 is equal to 1.197. And so our slope, our equation of best fit for these values is given here. This is our y-intercept, and this is our slope. Okay, so this is really just seeing if you understand how to use the formulas, creating the table, and plugging in the values. Okay, all right. On to example three now. In example three, it's very similar to example one, with the exception that we're looking for a quadratic fit. So at least squares fit to a quadratic polynomial. And so we want to develop that relationship using this relationship. Okay, so we have three parameters now. We have B naught, B1, and B2 corresponding to constant, linear, and squared terms. And so like the previous one, we're going to have three partials to take the derivatives of, which is what we did here. And we're going to find the critical values for each of these 3 points. We set each of those equal to 0. And then in the corresponding different colors to kind of help separate them out, you can see solving for each of the critical values. We have these relationships, okay? And so then utilizing the green, orange, and red relationships, we can then, just like in the previous example, rewrite as x is the sum, s double x is the sum of the squares, and plugging in each of the corresponding values after the sum. This is sx, this is n times b naught, b1 times sx, and then b2 times s double x. I didn't write there, but you know what this is. This is the sxy, b naught sx, b1 sx double x, and b2 sx cubed. So we have an x to the fourth, an s cubed, an x cubed. I think I forgot the x there. And then sx, and then of course this is the x squared y, so xxy. Okay, and so the summary of those relationships is here. And so just like before, they're linear in respect to the 3 parameters that we're trying to find. These terms not necessarily are linear, but they're just numbers. Okay, so we just need to calculate these numbers. So this is a matrix, a coefficient matrix. And we can do exactly that. We can invert this matrix and multiply it to solve for once we know what these number values are. And so that's what we did. And oh, yeah. And so that's what you do for those. However, computing this out would be obviously something that you would do in that computer algebra systems. Okay. And then in part three of example three, it wants us to consider a cubic regression. So it'd be the similar form. And based on our value here, so to compare, this is the quadratic, and this is the there we go. Yes. So here's the quadratic. And so you can start to see a pattern. It looks like in SX, S double X. So for a cubic, it makes sense then that we had to guess this would be S triple X. Okay, here we have SX and then S double X. So that's X, X double X, X triple X. So it would be an X to the fourth for a cubic. And then here this is SX, and then this is S double X. So it looks like it's growing this way. So the next one would be X triple X. This one would increase by one. This is second degree, this is third degree, fourth degree. So the next would be third, fourth, and fifth. So for a third degree, that's what we would expect based on the pattern of what we're expecting here. And that's what it asks us to do is we have to guess like what the form of the matrix would be. Um, that's exactly the pattern we're seeing that it goes up in order of the number of terms, right? The degree, if you will. So SS, XS, X double X, X triple X, and then it increases this way as well. And so this is the order here. Uh, the relationship here, I think you can see the pattern pretty. This is like x to the zero, x to the first, x to the third, second, x to the third. So we had a 4 by 4, then it would be next to the fourth s, x to the fourth y would be the relationship that you would expect to see for the given values, if you will, okay, or the known values. Okay. So notice the pattern from the flow the derivatives, and that's really what is being mentioned here from example two. Okay, so that's pretty much it for example three. Example four, and we're given some time, and we're asked to find a quadratic least fit to this data. So this is more of a computation problem, not a relational kind of problem. And so let's go ahead and look at that. So we want at least squares fit to a quadratic here. And so here's the data that we're given. And we derive the coefficients that we need. So Sx is 30, Sy is 230, Xx to the fourth is 15,664. These are just all the values. We don't need all of them, but just so we're for completeness sake. So here they all are. I found these I put them in a spreadsheet in GeoGebra, and that's how I computed the values, which then, of course, creates our matrix of this one. So the nice thing is once you kind of get your head wrapped around the formulation of what's going on, the computations with technology actually make these kind of fun, and they're pretty straightforward. So this is the matrix that corresponds to the one that we had. Is that an example three? Yeah, example three. So it's really this matrix that we're plugging in the values for. And so if I invert this matrix and solve for each of the constants, v0, v1, and v2, I should say parameters probably, then those are the values that we get. And it's interesting that v2 here is a pretty small number, right? That's less than a quarter, right? So it's a pretty small number, which means this coefficient for the quadratic term is really small. So the problem is really opening up. So it might be advantageous, or we might get away with, depending on the precision we need, that this could be a linear least squares and get a better approximation or a close enough approximation. So that's one thing to notice is like when do you know what order should you go out to, and if your leading coefficient is relatively small, that might be an indication that a lesser degree estimation is appropriate at that point. Okay. All right, that's example four. Example five we did in the notes, and so we'll jump to example six here. And so example 6 is a fun one. This one is a Graham-Schmidt ortho normalization here, or well, not normalization, but orthogonalization for the least square. And so it wants us to do it with the Legendre polynomials, so find the first five. And so you have to think to yourself, okay, so what's the weight and what's the interval of interest here? And so the weight function that we're going to use for the Legendre polynomials is actually just a constant one. And Legendre polynomials are defined on the interval from -1 to 1. Okay, so we'll use those to calculate the orthonormalization, orthogonalization. We're not normalizing these. Okay, so the B1, according to our theorem that we saw in the previous example, not example, but in the previous notes, we have the integral from a to b, which would be -1 to 1. The weight of x times the weighted function of 1 times p0 of x squared, p0 squared, over the integral from a to b of wx p0 squared. Okay, so that'll be our b1 term. And just looking out all of the b terms here, I have b2, b3, and b4. And so you'll notice how there's basically a pattern. So these are one less. So B3 is a P2, and then you have a P2 squared here. And then the C relationships are similar, but they're going to be a mixed product, if you will. So it'll be a P1 and a P0. It'll be a P2 and a P1, and these are always two less than the degree. So these don't start counting until the in value has gotten past 2. Okay. So then the combination of these two, so these are going to be a bunch of integrals that you compute in, well, I compute in GeoGebra. And so here is the rest of them. Okay. And then you may wonder, well, how do you build these p functions? What are those? And so those polynomials are of the form which were given in the theorem, right? So p naught is 1, p1 is x minus p1, which in our case would turn out to be just x. P2 is x minus p2 times p1 of x minus c2 times p naught of x. And so that turned out to be x squared minus 1/3. Wanted to write an x there, and that was my mistake. It was not an x. P3 is x minus b cubed here, times p2x minus 3c3 p1x, which is equal to x cubed minus 3/5 x. 4 is this form, and it came out to be this fourth order. And then p5 here as x minus p5 times p4 minus c5 times p3, and that reduces then to this value, okay? And so these are the first five Legendre polynomials that are orthogonal with respect to this weighting function over the interval from -1 to 1. In other words, if I use that product, the inner product, right? So this times this over times w over -1 to 1 would be 0. So you'd have to have p1 times p1 in order for it to be a non-zero value. And so in the next example, we're actually going to use these polynomials as a basis set to write out an approximation for the Gaussian, the unit, or the standard normal, if you will. So let's go ahead and look at that. If you're wondering like why or what would we use those for, or what are they needed for? So say we wanted to approximate the standard normal, e to the -x squared over 2 times square root of 2 pi, using the Legendre basis. Again, so these are the results from the example that we just did, example 6. And so our solution then is just to compute the corresponding coefficients. And so to do that, again, our interval is from -1 to 1, and our weight is 1. And so each of the corresponding coefficients have this form. So a naught is wx times p0 times f of x. And if you're familiar with Fourier series, for example, this has that very, very much the exact same idea, right? So this is, should have that feel to you, or if you have that familiarity, this should feel very similar in that regard. Okay, so here's A1, A2, A3, and A4. We don't need P5 in this example because we're only going up to fourth order. So we have each of these. So these were again calculated in GeoGebra, which my result will be linked there. And then, of course, the corresponding actual polynomial will be a0 times p0x, a1 times p1x, a2 times p2x, a3 times p3x, and a4 times p4x. And so the resulting actual calculation, of course, is in the linked GeoGebra calculation. So anyways, I hope that that helps kind of guide you through each of the problems in the one-a-days and give you some idea on how to attack or at least what to expect as you're going through the assignment. Okay, I hope that was helpful, and I'll look forward to seeing you in the next video.